We start with the Gauss Law, and we know in this case we are going to use the cylindrical Gauss surface. So we are able to derive this electric field. Second thing we know is the charge density Q over V, and in this case this volume is given by the area, which pi r square multiplied with L for the cylindrical case. So we get this expression. Finally, we find out this Q enclosed is written down here. We start with the A. In the case A, this R is between R1 and 0. So in this region is for A, we know this E will equals to Q enclosed over the 2 pi epsilon naught RL, and we substitute this thing inside. We get rho E pi r squared L over 2 pi epsilon naught RL. In this case, this small r actually will equals to the capital R, because this is not fixed. This is depend where we define the Gauss surface in the range given, which smaller than the R1. From here we can simplify it. We get this pi cancel out, and R cancel and L cancel. We get this rho E R 2 pi. This is the answer for A. Now we proceed to B. In the case B, this R is between this R2 and R1. You can see in this case we fully enclosed this internal solid non-conducting cylinder inside here. So in this case, this small r will equals to the R1. We get pi R1 square L over 2 pi epsilon naught, and this is the RL. Again, we simplify it. We get rho E R1 square over 2 epsilon naught R. This is the answer for B. In case C, this is between R3 and R2. So in case 3, this is the Gauss surface is somewhere here. Between this R3 and this R2. And one thing we know is that they have two region where from 0 to R1. So internal one, we will enclose all the charge. And the second part is from here to here. let's call this delta R, and between this R2 and this R1 here do not have a charge, so we have to add up this uh, the charge from this internal cylinder with the region of this volume of this R data. Now our E will equals to rho E, and this is pi R1 square L. This is for the internal cylinder. Plus this pi L is R square and minus R2 square. Well, this part is actually due to this delta R. This is over 2 pi epsilon naught RL. So again, the pi we can cancel out, and this L can be cancelled out. We get rho R1 square plus R square minus R2 square over 2 epsilon R. This is the answer for C. Let's go to D. In the case D, this R is greater than R3. So this is given by the outside here. This is a case D. In this case, we know this will fully enclose the both charge from this cylinder and also this concentric cylindrical tube. This is given by, the charge is given by rho E, this pi L, I think I can take out because this is just constant. This is R1 square is due to the internal cylinder, and this we have to add up the charge for this the outer concentric cylindrical tube outside here. This is given by R3 square minus the R2 square, because only in this region, like this in this case from here to here, in this region we have a charge, right? So in this region 0 to R1 we also have a charge, but between this R1 and R2 here don't have a charge, right? So we have to sum out here this the internal one given by this R1 square, and this R3 square minus R2 square will just give us the part, this outer the charge on this outer concentric cylinder tube. And to find the electric field, we divide O with 2 pi epsilon naught RL, and we can cancel this pi and this L. Finally, we get the rho E and R1 square plus R2 square plus minus R2 square over 2 epsilon naught R. This is the answer for D. This is E. E wants us to plot the E as a function of R, and the charge density is given. Also, this R1, R2, and R3 is given. So, charge density equals to 1.5 microcoulombs per meter cube. And R1 equals to 1 over 2 R2 equals to 1 over 3 R3. From here, we know this R2 is equals to 2 R1 and R3 is equals to 3 R1. Now we go to the graph. Here this ER, and this is, let's use the capital R. So from this 0 until the R1, let's refer back to the case A. You can see here this function is actually proportional to R, this charge density, and 2 epsilon naught is constant, so this E is proportional to R. That means this increased linearly with R like this until this R1, and our R1 is given by 5.0 cm, right? And let's find out this the corresponded electric field at this R1. We use the formula for the case A, which rho R in this case is R1 over the 2 epsilon naught. So this is equals to 1 by 10 to the negative 6, and we have a 5.0 cm over 2 epsilon. Here I get this is a 4.237 10 to the 4 Newton per coulomb. So the unit here we can write this is 10 to the 4 newtons per coulomb. So here is a 4.237. This is the R1. Let's consider this R2. So we know the R2 is a 2R1, which now we know the R1, so we multiply with 2, we get the 10. Now we take a look back to the this case B. You can see the function here is actually proportional to 1 over R. The rest is just a constant. That means in the graph, there will be something like this, brought off by 1 over R until the R2. Now we want to find out the correspond electric field as this R2. We refer to the case C here. Let's call this E2 and E. Now we know that this is correspond to the R2, right? So we make this R is equals to R2 in this formula. You can see we square this R, which make this R2 square. R2 square minus R2 square, you will get 0 at this part. The remaining actually is just R1 square, and below have and R2. Now here is given the R2 is equals to 2R1. We can write this is rho E R1 square over 2 epsilon naught 2R1. Now we can simplify it. We get a 1 over 2 rho E R1 over this 2 epsilon naught. You can see actually the value here is this value here. We already calculate, which is equals to this E1. So this is 1 over 2 and 4.237 10 to the 4. This is just half of this E1. So this correspond electric field is given by 2.1185 10 to the 4 Newton per coulombs. We write down here 2.1185. Now we will need to consider this until the R3. This is R3 is equals to 3R1, which given by 15.0, and this is the R3. So in the case for this R2 until R3, we take a look back to this C. You can see here only the R is the variable, and the rest just R1, R2, and this charge density is rho naught 2 is others is just a constant. So you can see here we square this R and at the denominator we divide it. We will expect the graph will look something like this. This is the R3, and it will reach a peak somewhere when this is equals to R3. Now let's find out the correspond electric field. We are going to apply the same formula, but in this case, we make the R equals to the R3. So E3 will equals to this rho E and R1 square plus R3 square minus the R2 square over 2 epsilon naught R3. Now we make all this R R3 and the R2 in terms of the R1. We know this R3 is equals to 3R1 and R2 is equals to 2R1. Now this let's divide by 2 pi epsilon naught and this is 3R1. So R1 square plus 9R1 square minus 4R1 square over 2 epsilon naught 3R1. So here is rho E. We get the 6R1 square over 2 epsilon naught and 3R1. We can cancel out this R1 in the denominator. Now the remaining is here this we get 2. So we have a 2 rho E R1 over 2 epsilon naught. Now here you can see this part here actually is just equals to E1. That means you can directly use the answer we calculate for E1 multiply with 2. We get this is at 4740 Newton per Coulomb. Now we find our answer at this is equals to 8.474 10 to the 4 Newton per Coulomb. So here this is 8.474 8.474 and now until here this is R3 R so let's say here is 20 cm and you can see after this R is reached R3 we need to follow the D here which R is greater than R3. You can see this case is we get the 1 over this R. That means the electric field start from this r greater than r3 is 4 off by 1 over r. So we get back, because you can see the rest is just a constant, right? So we get back the curve like this. So this is the answer for this question.